Today we're going to be transforming absolute value functions, and to begin with I'd like you to take a look at two linear equations graphed. They are y equals negative x and y equals positive x. If we want to graph this red function over on the right, we can take a piece of the blue and a piece of the green and we can write it as a piecewise function. We want to graph y equals negative x when x is less than 0, and we want to graph y equals positive x when x is greater than or equal to 0. These piecewise functions can be blended into one by what's known as the absolute value function. The points that are graphed there remind us that the function of an absolute value is to turn what's on the inside positive. So the absolute value of negative 3 is positive 3, the absolute value of 2.7 is 2.7. The absolute value of 0 is 0, and so that takes us to something called the domain and range, two notions that we're going to be using throughout this year. The domain are the possible inputs, and so a negative way to think about this is, are there any restrictions on the domain? Is there anything that x cannot equal? We can take the absolute value of anything, so in interval notation we go from negative to positive infinity. Conversely, for the range, it's all of the possible values that come out of the function. So it's the output. The lowest possible number that could emerge is 0 because the absolute value of 0 is 0. And so we range from 0 to infinity, but if you notice in interval notation we put a hard bracket on the left because 0 is a possible value. To transform a function, we're going to use one or a combination of four variables, a, b, h, and k. And throughout this year, we're not only going to be transforming absolute value functions, but also quadratics and cubics and rationals and radicals and logarithms and lots of different functions. So I'm going to use also today a generic f of x. We're specifically talking about absolute values, but keeping f of x in mind is going to help. A quick word about letters. F clearly stands for function, and so to say f of x means we're going to talk about a function, but g of x, g is the next letter that follows in the alphabet, and if we're talking about transforming, we need to transform something that came before it, so g of x is logical. Alphabetically, a is the first letter. It comes first in our function. It also stands for amplitude, so that's convenient. And it's going to be a vertical stretch if the absolute value of a is greater than 1. It's going to be a shrink if that value is between 0 and negative 1. And it's going to be a reflection over the x-axis if a is negative. Alphabetically, the next letter is b, and so a horizontal stretch or shrink or reflection is b, and it has a reciprocal nature to the amplitude. We'll see specific values or examples in just a moment, but if the absolute value of b is between 0 and 1, that's a horizontal stretch, whereas if it's greater than 1, it's a horizontal shrink. And it's a reflection over the y-axis if b is negative. H stands for horizontal, very nicely, and if you notice that the function has x minus h. If it's x minus 2, then 2 is positive and we move 2 units to the right. If it's x plus 5, that can be rewritten as x minus negative 5, and that would refer to a shift to the left. We're not going to use I and j because the I stands for a specific number. It's the square root of negative 1, and an italicized I and an italicized j can look the same or similar if we're sloppy. So we go to the next letter, k, to talk about a vertical shift. So I'd like to begin transforming some functions here, looking specifically on this slide at values of k. We're going to take the absolute value function, the parent function, and we're going to shift vertically, either up or down. So if we take that parent function and add 4 to it, plugging in a 3, 3 plus 4 is 7. Plugging in a negative 2, that's going to be a positive 2 plus 4 is 6, and plugging in a 0 will give us 0 plus 4 is 4. There's no restrictions on the domain. We go from negative to positive infinity, and our range goes from 4 to infinity. For a second function, what if we shift down 6 units? Let's just plug in some values. 6 minus 6 is 0. A negative 10, take the absolute value as positive, then subtract 6 will be at 4. And g of 0 minus 6 would be negative 6. Our domain is still unlimited, but our range is going to get as low as negative 6. Let's take a look at the graph and see if we can make sense of these, including the range. The parent function is in red, and the first function is the one above. We've shifted up 4 units, and you can see those 3 points graphed. Notice that for as much as you can go from left to right, from negative to positive infinity, we'll never get below 0, negative 4. We have a y value of negative 4 as our minimum value. So our range goes from 4 to infinity, and therefore I hope you can see why the range for the second function is from negative 6 to infinity. Let's turn our attention now to the a value, the amplitude. So again, this is a vertical stretch, shrink, or reflection. First example, what if our amplitude is 7? We still want to plug in any value in the world for x, take the absolute value, multiply times 7. When we do that, no restriction on the domain, but we're going to run from 0 to infinity. Here's an example. You can see where 1, 1 was a point on the red graph. Now 1, 7 is a point on the green because we've stretched up 7 units. Second example, s of x, just a different function. G of x is just a dummy function. Here's s of x. Our amplitude is now 1/3. That's a value between 0 and 1, so it should be a vertical shrink. We haven't changed the domain or range. It's still the same, but we're going to be stretched downward. So instead of being at 6, 6, we're now at 6, 2, because we've taken that 6 and divided by 3. Here's a third example. What if we throw in just t of x equals the opposite of the absolute value? Remember, the absolute value function is to turn things positive, but this negative is on the outside. Now, the negative is a reflection over the x-axis, so please take a second to look at this range. We're going to run from negative infinity up to and including 0. What does that look like on the graph? It's a perfect reflection of the red graph over the x-axis. So where 4, 4 was a point on the original, the pre-image, now 4, negative 4 is a point on this one. And finally, what if we have some combination? What if our amplitude is negative 2? You should think of two things happening here. We're going to vertically stretch, but also reflect over the x-axis. So just like the last one, our domain is going to run from negative infinity to 0, and we're going to look like this. It's vertically stretched, just like the 7 was, but not as strong. It's not 7, it's 2. It's a reflection over the x-axis. So instead of being at 4, 4, it flipped over to be at 4, negative 4, and then it's stretched. Or you can think of it stretching up to 4, 8, and then reflecting. Now let's perform a composition. Let's do both stretches, shrinks, and reflections, as well as shifts. So here's our function. We're going to have an amplitude of negative 1/2, and we're going to have a k value, a vertical shift of 5. I'd like to just plug in a few values and see what comes out. Check to math and see if you agree with these. We have shifted up to 0, 5, but we've reflected over the x-axis. So when we graph this thing, it's a horizontal shrink, so it looks wider than the parent function. It's reflected upside down, but it shifted up 5 units. So although these rays look like they're pointing downward, which they are, we generally speak from smaller to greater numbers, so the range comes from negative infinity up to 5. Second example, if we take a positive 2 for our amplitude and a negative 1, then we're going to vertically stretch this thing but shift down 1 unit. Here are just a couple of values that are going to find themselves as coordinates on the graph. And when we plot this into the coordinate plane, we'll see that our vertex has gone from the origin down to 0, -1, but we've vertically stretched. And you can relate those coordinates -3, 5, and 4, 7 on the graph. Now we're going to turn our attention to horizontal shifts. Stretches, shrinks, and reflections in just a moment, but shifts right now. That's the blue h, and remember, it's x minus h. That's an important thing to keep in mind here. So if we say x minus 5, that 5 is positive, and it's going to be a 5-unit shift to the right. Here are just a couple of values that we can plug in, 5, 3, and 7. If we take 5 minus 5 is 0, our input was 5, our output was 0. Our input is 3, our output is 2, our input is 7, our output is 2. So 5, 0, 3, 2, and 7, 2 are points on our graph. If we talk about domain and range, this entire time our domain is going to be unlimited. But our range, we did not shift up or down, we did not reflect. So we're going to still have a range that goes from 0 to infinity, just like our parent function. So we've shifted 5 units over to the right. You can see some symmetry here. Our lowest value for y is 0, and we go up towards infinity. A second example, just some dummy name for the function. This is p of x. If we're going to make this transformation something where we say x plus 4, that could be written as the absolute value of x minus -4. The -4 tells us we're going to shift 4 units to the left. And I just have a few examples here of values we can plug in to check. Again, we did not do any reflections here. So when we graph this thing, our purple function has gone from the parent function with the vertex at the origin 4 units to the left. You can see anytime you plug in 0 for x, you're going to get your y-intercept. So 0, 4 is our y-intercept, -x, 0 is our x-intercept, and -7, 3 is just any old point. It will probably be helpful to talk about the horizontal stretches, shrinks, and reflections that come to us through the variable b if we juxtapose it with the amplitude. So let's see what happens when we have g of x equals 4 times the function, and t of x is the function with that 4 multiplied inside the absolute values. The 4 on the outside is bigger than 1. That's going to be a vertical stretch. The domain is unlimited, and we're going to run from 0 to infinity. So there's your function. Now, how does that compare to t of x, where the 4 is on the inside? Notice also that we went from 1, 1 up to 1, 4, a stretch of 4. The t of x, with that 4, that's a value greater than 1. That's got that reciprocal relationship, so it's going to be a horizontal shrink by a factor of 1/4. The domain is still the same. When we graph this, it looks the same, except we went from 4, 4 to 1, 4. The purple and orange graphs were mapped on top of one another, but they came from different perspectives. If you can think of the origin as being like a thumbtack is on there, we take the red parent function, and in purple we pull both rays upwards, so we're stretching and we're going away from the x-axis, whereas in this one with the orange, the y-axis running vertically there is almost like a magnet, and it's taking the parent function and it's drawing it in by a factor of 1/4. Now what happens when we deal with negative values? The amplitude in g of x is a -1/2. The first thing to consider there is that it's a vertical shrink. So we're going to go in our graph from 4, 4 down to 4, 2. For t of x, the 1/2 is a horizontal stretch. We take the reciprocal of b and we say that it's a stretch by a factor of 2. So we go from 4, 4 out to 8, 4. Now let's deal with the negatives. In the g of x, it's a reflection over the x-axis, so we go from 4, 2 down to 4, negative 2. In t of x, it's a reflection over the y-axis, so we go from 8, 4 to negative 8, 4. Now that doesn't, in the orange here, you can't really tell the difference because it's centered right on the y-axis. So when we reflect over it, it's just mapping onto itself. For the first one, we flipped over the x-axis, so our range goes from negative infinity to 0, and we stayed consistent for the orange, so we're going from 0 to infinity. Let's perform a composition of transformations here. You can see it already graphed over on the right. First of all, in order of operations, PEMDAS, we'd like to deal inside the parentheses first, and x minus 6 tells us that we want to move 6 units to the right. So you can take the vertex at 0, 0 and shift it over to 6, 0. You can also take that point up at 5, 5 and shift it 6 units to the right to wind up at 11, 5. Secondly, when it comes to multiplying and dividing, we're multiplying by a 2. That's inside the function. That's a b value, and it's a horizontal shrink of the reciprocal of 1/2. It's the reciprocal nature with the amplitude. And so if that vertical line, x equals 6, contains the vertex, we are horizontally shrinking toward that. So halfway between x equals 6 and x equals 11 is x equals 8.5. So 8.5, 5 becomes a point on our graph. We come back to there. Our domain is still unlimited, and our range still runs from 0 to infinity because we haven't reflected over the x-axis, nor have we shifted up or down. Another example of compositions of horizontal transformations, we have our parent function, which is the absolute value of x, but we insert a b value of negative 1/3, and notice it should read x minus h, but I have an x plus 4. I want to take a little bit of time to rework that so it reads x minus negative 4. That tells me I want to shift 4 units to the left, and I also want to reflect over the y-axis and stretch by a factor of 3, which is the reciprocal of 1/3. When we look at the first graph, we take the parent function in red and we shift 4 units to the left, so you can see the vertex at the origin 0, 0 has slid to negative 4, 0, and also the point at 5, 5 has gone over to 1, 5. Also, if we start to look at the negative, we can see how a reflection, we want to say that it's a reflection over the y-axis. It's a reflection over that line of symmetry. So 1, 5 gets mapped over to negative 9, 5, and negative 9, 5 gets mapped over to 1, 5. And then finally, when we consider that stretch of the 1/3 reciprocal, from that line of symmetry there, you can see how we go by a factor of 3. And our final example for this PowerPoint is to look at all 4 things together. With all 4 variables, if you notice the color coding in my g of x function, you'll see that my 2 is not blue, and that's because I'm missing a set of parentheses. It's 1/5 x minus 2. What I want to do is draw the 1/5 out so I get the parentheses. That's a common mistake to think that you're going to shift 2 units to the right, but the 1/5 actually plays a role in this. We're actually going to shift 10 units out. Now that we're in that position, if the 10 is positive, then we should shift 10 units to the right, and you can see that example. And I want to hold on to that vertical line x equals 10, because when I deal with my next value, b of 1/5, we're going to talk about a horizontal stretch by a factor of 5. So from that vertical line at x equals 10, 11,1 is a point on my blue graph, and 15,1 is a point on my orange graph, because I've gone out by a factor of 5. If I consider my amplitude, I want to break it into two parts, and the first thing is I want to consider the number 3. That's talking about a vertical stretch, so I should be looking that it's going from a point like 15,1 to 15,3 because we are stretching up by a factor of 3. And I also want to consider that there was a negative in there. So now I want to reflect vertically, in this case over the x-axis, and I should have this look. It's a little bit different, change the orientation here a little bit, but we're going from the dotted graph with 15,3 as a point. Now reflecting over the x-axis, we're at 15, -3. And finally, that 7, in order of operations, we're now adding or subtracting. We're shifting up 7 units, and so we should look like that. We've taken a point 15, -3, and if we shift up 7 units, we get to 15,4. And perhaps more importantly is that vertex, which is now located at 10,7. Look at the blue 10 and the black 7. That is where our vertex is located. You might remember HK is the center of a circle from geometry. We're going to have vertex notation with parabolas real soon. And once again, just to finish up with domain and range, you can plug in anything you like for the domain, but our range is going to be any value from -infinity all the way up to and including +7.